now I think that we will just be able to conclude the course in the next lecture. So, this is our penultimate lecture. So, let us just go over what we covered in the last class. Now, what I have done is I have taken the last lecture and so this is an internal thing. I would like to make these notes for 40 and 41 blend into a single file. Okay. So, it does not really matter since you will have access to the file in either case, but now I rather than separate the lectures I have combined them and I have actually given it a slightly different title from what I had before. So, the title is a transform approach to cyclic codes. And so, what we did last time just to hit the highlights of our last lecture was basically we said look, we are going to discuss cyclic codes and our viewpoint of cyclic codes is going to be from the point of view of transforms. The particular type of transform is called a finite field transform. So, first we said, well, we need a little bit of machinery in order to start talking about transforms, and we needed that in particular that element alpha. So, if you have a code over an alphabet of size q and the block length is n, then you need to find a finite field that contains your original field that contains an element of order n, because your original field may not contain such an element. So, you have to expand the size of your field. Okay, so, once you did that, you have the element alpha, then we went ahead and defined the finite field transform, and then we went about examining its properties such as linearity, cyclic shifts, inversion, convolution, conjugacy. Once we had understood or reasonably had a reasonable understanding of excuse me of the transform, then we went back and said, okay, our interest is in cyclic codes, by which we meant we are interested in block codes having the property that they are linear and they are cyclic, they are closed under cyclic shifts. And we were adopting a transform viewpoint of these codes. So, towards that, and I think we just about got started over there. So, I think so let me take up the discussion on cyclic codes and lead you a little bit slower through that, since we will be continuing that discussion in the present lecture. So, here are some of our slides on cyclic codes. So, we defined what it means to be a cyclic code, and then we put an equivalence relationship. So, we said that when we take a code word and we look at its transform, then those subscripts lambda which appear in the transform we will regard as frequencies. So, then we defined an equivalence relationship on the frequencies, which led to organizing them according to cyclotomic cosets. So, here is an example. Then the smallest element in each coset is called its coset leader. Then we defined the notion of a closed set of frequencies, that is, a set of frequencies is a closed set if it is closed under multiplication by q modulo n. And an easy way to actually picture this is that a closed set is precisely the union of cyclotomic cosets of q cyclotomic cosets mod n. Okay. So, then so that for example, here if you go back here, then any closed set is just a union of certain of these cyclotomic cosets. Then we introduce the notion of the null spectrum of a code. The null spectrum of a code is those collection of frequencies at which every code has transform value equal to 0. And I gave you an example here and said that actually this is the general picture of cyclic codes. That is, that you organize given a cyclic code, given an alphabet size q, given an element n, you find a field that contains a primitive element alpha. Then you organize the frequencies according to these cyclotomic cosets, the q cyclotomic cosets mod n, and then you pick a closed set as the union of certain of these cyclotomic cosets. For example, you might pick the union of these two, and then you say I am going to insist that my code words have transform value equal to 0 on these elements, and outside these I do not care. Because of conjugacy, if you insist that the transform is 0 at frequency 1, then it is automatically going to be 0 at all these other frequencies. Okay. And so, the design of cyclic codes in some sense is just a matter of either including or excluding cyclotomic cosets from inclusion in the null spectrum. So, that is why there are only 32 codes, for example, having block length 15 over the finite field of 2 elements. And that is about where we had left off. So, I think what I will do is I will begin our lecture. Let me just insert a page and put in a quick summary. Okay, so this is a rather quick summary of what we did last time. We looked at finite field transforms. The first was the expansion of the finite field to find an element of order n. Then we gave the formal definition of the transform. We looked at its properties. We started discussing cyclic codes. We discussed cyclotomic cosets, closed set. So, I think these two got interchanged in their order here. So, perhaps just make a note of that in terms of the order in which we discussed them, and then finally we introduced the notion of a null spectrum. Now, we want to proceed with the theory of cyclic codes, and our goal, as the title says, is to actually estimate the parameters of a cyclic code. So, what do we mean by the parameters? Well, the block length is clear, the alphabet size and the block length are clear. So, what is of interest are the other parameters, namely the dimension of the cyclic code and its minimum distance. So, those are the two things that we are going to target in this lecture. So, the first result we will show today is that the null spectrum of a cyclic code is a closed set. Remember, what we mean by the null spectrum of a cyclic code is that it is those collection of frequencies where every code word has transform that evaluates to 0. Okay. So, the proof actually starts from there. So, here if lambda belongs to the null spectrum of the code, then that implies that C hat of lambda is 0 for all code words. But if C hat of lambda is 0, then C hat of lambda raised to the qth power is 0. But then by the conjugacy relationship, C hat of lambda raised to the qth power is C hat of lambda q. The reason being that your code word belongs to the ground field, and whenever you have a code word that belongs to the ground field, its transform will satisfy the conjugacy relationship. So, that forces this equal to 0. But then, so this means that if lambda belongs to the null spectrum, so does lambda q, and hence this is a closed set. So, hence the null spectrum of the code is a closed set. All right. Second lemma. Then, so what we actually said is, given a code, we said we are going to let the set of all frequencies where the code word transforms the value to 0, then that is a closed set. There is a converse, sort of converse of this, and says, look, supposing on the other hand, if I started out with a set of frequencies which was closed under conjugation. So, S is a closed set of frequencies, and if I then define my code to be all n tuples whose transform evaluates to 0 at all frequencies contained in S, then that in fact is a linear cyclic code. Okay, so, it is kind of a converse. It says that I can start from a code and I can go to a closed set, or I can start from a closed set and I am led to a linear cyclic code. So, let A of t and B of t be code words, then so that means that A hat of lambda, B hat of lambda are both 0 for all lambda in the closed set. But then that is also true if I take a linear combination of them, where theta belongs to fq, and so that means that, but then by the linearity property of the transform, this quantity here is the transform of A t plus theta b t. Okay. So, that means that if A t and B t are code words, so is A t plus theta b t. So, that proves that your code is linear, which is not surprising. Okay. So, basically we have used the linearity of the transform to prove that the code is linear. Next, if the code, if C t is a code word, so it only remains to actually prove that this code is not only linear, but it is also cyclic. So, we have to now worry about cyclic shifts. So, here supposing C t is a code word and you define A t to be a cyclic shift of C t, and you take the transform of A t, that is alpha to the lambda tau C hat of lambda. But then since C hat of lambda is 0 for all lambda in S, so is A hat of lambda. But then you defined your code word as the set of all vectors whose transform is 0 on S, right. And so that automatically means that A of t, that it means that A of t is also a code word, and therefore the code is cyclic. Okay. So, we basically the way we prove this is just by using the property of the finite field transform under cyclic shift. You just get a multiplied, the transform values are just multiplied by some constant. So, it does not change the fact that the transform is 0 at certain frequencies. For this reason, the code is closed under cyclic shifts. Now, just a reminder here, reminder slide here to say that in all the subsequent discussion, we will be working with a set of parameters, standard parameters. So, this is the common setting. Q will always denote a power of a prime, and then n will be a reference to the block length, and we will always have that q and n are relatively prime. Small m is going to be the order of q modulo n, and C will be a cyclic code of block length n over fq. So, in this setting we are going to define something that is called a basic sequence. A basic sequence of frequency lambda naught, where lambda naught lies between 0 and n minus 1, is a sequence satisfying that b hat of lambda is 1 whenever lambda is either lambda naught or else a conjugate of lambda naught, meaning that it is some power of q times lambda naught, and it is 0 everywhere else. For example, here is the case when so this is the case when q is 2 and n is 15 and m is equal to 3 in this case. Oops, that should be m is equal to 4, pardon me. So, supposing I pick lambda naught to be 3, okay, then what I want to illustrate is a basic sequence of frequency lambda naught, meaning its transform value is 0 everywhere except at frequencies corresponding to lambda naught and its conjugates. So, that means that this b of t is sequence has transform which is 0 on all these cosets, and it is 0 every and are all cosets other than the coset corresponding to 3 and here it is 1. Now, the conjugacy also tells us that its value at 6 is 1 to the q is 1 times 1 to the q, which is still 1, and so on. So, it actually takes on the same value for every element within a coset. It takes on the value 1 for all the elements in this particular coset, and it takes on the value for everywhere else. Okay. Once again, that is because if b hat of 3 is 1, then b hat of 6 is b hat of 12 equal to b hat of 9 is 1, because b hat of 6 recall, I will put this on the side here, b hat of 6 is b hat of 3 squared. So, for this reason, if b hat of 3 is 1, then b hat of 6, which is its square, is also 1. Okay. So, this is going to clutter this. So, let me erase this. All right. Now, the next lemma says that if C, so it's now we are exploring the connection between closed sets and cyclic codes further. So, let C be a cyclic code whose null spectrum is given by this. Then it is telling you that really there is only one code that can have this null spectrum, namely it is that code which corresponds to all vectors, all n tuples over f q whose transform values are 0 at every frequency in the null spectrum. Okay, so, we started out by saying C is some subset of f q to the n whose transform values are 0 at all frequencies in the null spectrum. But it turns out that the linearity and cyclic properties that C possesses cause C to in fact be precisely the largest possible collection of vectors that you could have when you just impose the constraint on the transform values. Okay. So, in this sense, given a null spectrum, there is a unique code that is associated to it, and in particular the basic sequence of frequency every frequency lambda not in the null spectrum belongs to the code. Okay. So, that is a side comment. I think I will ignore that for now. I do not believe the way I am presenting it that we will call upon it. If I need to, I can always come back to this. Okay. The proof is in the appendix, so I will not actually go through that. Okay. So, once again let us recap the three lemmas that we have. The first lemma says that the null spectrum of a code is a closed set. The second lemma says that the set of all vectors whose null set is a closed set, whose null spectrum is a closed set, is actually a linear cyclic code. The third one says, well, I can actually say something stronger. In fact, I can actually say that if you tell me that a code has a certain null spectrum, I can actually tell you which code it is, because there is essentially just a single code for a given null spectrum, okay, and that is precisely the set of all n tuples which possess the null spectrum, because that forms a cyclic code. And it turns out that any cyclic code within this null spectrum is essentially this one. Okay, so not surprisingly, when you put these together, you have this important null spectrum theorem which says that there is a one-to-one correspondence between cyclic codes over Fq of block length n and closed sets of frequencies. Okay. So, what is the correspondence? The correspondence is just this, that on the left side what you have is the collection of all cyclic codes of block length n over Fq. Okay, so, let us note that. By the way, just a reminder, whenever I say cyclic code, I will mean linear and cyclic. That is the common usage. So, the linearity is sort of taken for granted. So, when you talk about a cyclic code, you really mean a linear cyclic code. And on the right side here, what I have is the collection of all closed sets. Okay. So, these are the two sets on both sides, and then to show the one-to-one correspondence, you just pass from a code to a closed set by just looking at its null spectrum. Given a code, you identify the null spectrum. We know that from one of our earlier lemmas that it is a closed set, and so that makes this mapping actually makes sense, and it is one-to-one and onto because of the properties that we proved in lemma 1 to 3, because I mean what you have to show is that it is onto and one-to-one. To show that it is onto, you got to show that given a closed set that there is a cyclic code associated to it, but that is clear because you just look at the set of all vectors whose transform value is 0 on that closed set, and you will get a linear cyclic code. And furthermore, that cyclic code will have null spectrum exactly the closed set that you started out with. So, it is onto and it is one-to-one because two different codes cannot have the same null spectrum. We have just seen that the null spectrum for a given null spectrum, this is essentially one code. Okay. So, it is really a consequence of our lemmas 1 to 3 above. Okay. But the important thing is that we are clear that clear about what this one-to-one correspondence is. And let me just again go back to this earlier example we had. And so once again, so now I think you will perhaps have a slightly better understanding of what I was saying earlier. Earlier I was saying that look, picking a cyclic code is exactly the same as picking a bunch of cyclotomic cosets and saying I am interested in all those vectors whose transform values are 0 for every frequency which is in the union of those cyclotomic cosets that you just picked. So, it turns out that the particular selection of null spectrum here corresponds to a double error correcting BCH code. All right. Okay, good. So, now that we have this correspondence between cyclic codes and closed sets in the frequency domain, we can now start talking about the parameters of these codes. So, the parameters that are of interest are two. One is the dimension and the second is the second property that is of interest is its minimum distance. And this theorem actually is telling us that the dimension is precisely the set of frequencies outside the null spectrum. So, since the null spectrum is of size ns, the dimension is n minus the size of ns. So, I think let me just make a correction here, that should read ns C. The proof is in the appendix. Perhaps what we will do is we will just look at an example. So, here is an example. This is our familiar example by now. Q is 2, n is 15, and our null spectrum has been chosen to be the union of these two cyclotomic cosets. The null spectrum has to be a closed set. So, it has to be a union of cyclotomic cosets. We have chosen these two. So, that is indicated by the presence of these zeros. This star means that the transform value here can be either 0 or non-zero, and you give it full freedom. And the theorem that we just read out just now, this theorem says the dimension is simply the number of frequencies that do not belong to the null spectrum. So, here there are 15 frequencies in all, 8 of them belong to the null spectrum. So, the number of frequencies outside is 4 plus 2 plus 1 is 7. So, the dimension of the code is actually 7 in this case. Then we have a weight theorem. Okay, so, the two parameters that we were interested in, one is the minimum the dimension of the code, the second is the minimum distance. Okay, so, now we are trying to establish the minimum distance of the cyclic code. So, the weight theorem says let C of t be an n-tuple whose Hamming weight is w. Okay, now, it is not necessarily a code word, it is just any n-tuple. So, this is a rather general property. Then so, I am just thinking that perhaps I should change the notation from C of t to A sub t, so that there is no confusion and it is clear that this applies in general. Okay, so, let me make that small change. Let A t belong, so this is A, 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 A. Okay. So, let A t be any vector whose Hamming weight is w, then its transform value satisfies a linear recursion of degree w in the frequency domain. So, what does that mean? It means precisely what this equation says here, that is, you can recover the transform values at any frequency lambda by looking back in the past at the past w values of the transform. So, a hat of lambda is some linear combination of a hat of lambda minus I for I ranging between 1 to w, and these coefficients ui are in f q to the m. Once again, in the interests of moving along, I have left the proof in the appendix. What we will do is, however, see an application of this theorem. So, this is a key theorem in cyclic codes, and it says that supposing C is a cyclic code over f q of length n, where n and q are relatively prime, and let us assume that the null spectrum contains a stretch of consecutive frequencies that is, you have a starting point m0 plus 1 up to m0 plus d minus 2. So, the number of consecutive zeros in this particular case is d minus 1. So, this is obviously a subset of the set of all frequencies. Actually, this should have been n minus 1, let me correct that. And here these there is freedom in choosing m0. So, m0 is some integer and d is some integer, also an integer which is greater than or equal to 2. And excuse me, it says here that m is the multiplicative order of q mod n, but since that does not appear in the theorem now, I am just going to delete that. So, the assertion of the theorem is that the minimum distance of the code is in this case greater than or equal to d. So, just a quick remark here, and not a part of the theorem, but just a quick comment. D is called the design distance of the code. And so, the minimum distance of the code is at least d, and therefore, the parameters of the code, the block length is n, that is obvious. The dimension is n minus the size of the null spectrum, we covered that in the previous theorem, and the minimum distance is greater than or equal to d, which is the content of this theorem. The proof is actually quite straightforward, so we will go through with it. So, since C is a linear code, it is enough to show that the minimum Hamming weight of a code is greater than or equal to d. This we proved in connection with binary codes. We showed that in the case of binary codes, the minimum distance is equal to the minimum Hamming weight, but that proof also extends to the non-binary case. That is, the minimum Hamming distance of a linear code over any finite field, that is, whose symbol alphabet is any finite field, has the property that the minimum Hamming weight is equal to the minimum Hamming distance. Okay, the minimum non-zero Hamming weight is the minimum Hamming distance. So, now supposing you have a code word, and let us say that its Hamming weight is w, and let us assume that w is greater than 0, okay, because we are trying to estimate the minimum distance, and we know that the code contains the all 0 code word, and when we talk about minimum Hamming weight, we are interested in the minimum non-zero Hamming weight. So, we will assume that w is greater than 0. Then our earlier lemma that we just read out says that the theorem says that if a vector has Hamming weight w, then its transform satisfies the linear recursion of degree w. Okay. So, because of this, therefore, C hat of lambda satisfies the linear recursion of this form. C hat lambda is the sum I is equal to 1 to w, C hat of lambda minus I ui for all lambda. So, in particular, what that means is that if you put lambda equal to m0 plus d minus 1, okay, where did I get that from? Well, all that I am doing here, so maybe I can actually at this stage draw a picture before continuing with the proof. Okay. So, let me insert a page here. So, the picture is like this. So, let us look at your transform C hat of lambda, and let us say that these are your indices. You start with 0, 1, and then somewhere you encounter m0 plus 1, m0 plus d minus 2, m0 plus d minus 1, m0 plus d on up to n minus 1. Let me see if I can group this better. So, let us say these are the frequencies, and when you look at C hat of lambda, we know that since this is the null spectrum, this is included in the null spectrum. So, it is contained in the null spectrum of the code. Because of that, when you look at C hat of lambda, you are going to see a 0, a 0 and a 0. You are going to see d up to here. Yeah. So, sorry about that. The string of consecutive zeros only runs from m0 to m0 plus d minus 2. Let us go back and check that. So, you see that it goes from m0 all the way up to m0 plus d minus 2. So, we know that the transform is 0 out here, and in general we do not know what the transform values are outside. So, I can actually put some star values in here. Okay. But we do know that C hat of m0 plus d minus 1 so if you pick in particular with C hat of m0 plus d minus 1, let me do one thing. Let me pick this relationship and bring it down so that we can talk about it while looking at the figure. Okay, here. So, let us look at this expression here. Okay. And so, picture this, that you are saying that the transform value at frequency m0 plus d minus 1 is some linear combination of the ones that came before it, okay, the w terms that came before it. But if w is less than d, then since you are going back up to m0 plus d minus 1 minus w, this is at most m0 plus d minus 1, you are going back into the past. The earliest or the smallest index is this minus d minus 1. So, the w can be at most d minus 1, since we are assuming it is less than d. So, this comes out to m0. So, that means that what you actually shown is that if it has weight w, then this value must be linear combination of these zeros, which means that this entry must be 0. Now, you move over here. This one must be a linear combination of the preceding I guess d minus 1 terms, and is again 0, and so on. So, what it says is that if you have a string of d minus 1 consecutive zeros and you have a linear recursion whose degree is d minus 1 or less, then you are going to, this string of zeros is going to extend all the way around until you get the all 0 code word. So, what that proves is that every code word must have Hamming weight W which is greater than or equal to D, because the only way it can have Hamming weight less than or equal to D minus 1 is if it is in fact the all 0 code word. Okay. And that proves that which contradicts our assumption that W is greater than 0. Therefore, W is greater than or equal to D, and hence D min of the code is greater than or equal to D. Okay. So, that completes our derivation of the parameters of the code. So, now we have the parameters of our code under control. Next, what we will do is let us examine two classes of codes. Okay. We will look at an example of BCH codes. So, the BCH class of codes falls into the class associated with this theorem. Okay. So, BCH codes turn out to be codes having a null spectrum which contains a consecutive set of frequencies. Here Q is equal to 2 and n. So, for the primitive case n is of the form 2 to the m minus 1. So, actually if you start out, perhaps I should start out, supposing I said that it is 2 to the e minus 1, then this means that the multiplicative order of or actually let me put back the m here. So, if n is 2 to the m minus 1 and then you ask what is the multiplicative order of q mod n, and then you will see that it is actually equal to m. Okay. So, this implies that the multiplicative order of q mod n is equal to m. So, I will leave that as a small exercise for you to check, it is quite straightforward. Okay. And so, and then the null spectrum is, the null spectrum of the code is required to contain this consecutive string of frequencies. Therefore, a BCH code, therefore binary BCH codes have parameters n is equal to 2 to the m minus 1 and the dimension is n minus the size of the null spectrum, and d min is greater than or equal to d. Okay. Now, it turns out that a popular choice choice is m naught equal to 1. So, that means your consecutive, therefore, in which case your null spectrum contains 1, 2 all the way up to m0 plus d minus 2, which is d minus 1. So, you have a consecutive stretch of zeros from 1 to d minus 1. Then so what I am trying to get at is the following. Here in describing BCH codes, I have given you the length and the minimum distance, and I have left the dimension expressed in terms of the complement of the null spectrum. The catch here is we do not really know what the null spectrum is, because all that we know is that it contains these frequencies. We do not exactly know what it is. So, that leaves a question mark over the dimension of this code. Now, you can't completely erase that, but what you can do is, in this particular case, you can estimate or at least lower bound the dimension of this code as follows. So, let us say that m0 is 1, in which case the string of consecutive zeros actually ranges from 1 to d minus 1, which can be rewritten as 1, 2 all the way up to 2t if d is equal to 2t plus 1, because typically when you are looking for error correction, then your minimum distance is 2t plus 1. For example, if you want to correct 2 errors, you will make your minimum distance 5 and so on. Okay. So, this is a popular situation that you are likely to come across. So, what can you say in this case? Then note that in the two cyclotomic cosets, to make it clearer, let me call this, in the Q cyclotomic cosets mod n, i.e. in our case this simply amounts to the two cyclotomic cosets mod 2 to the m minus 1 the size of a cyclotomic coset is at most m. Okay. Let me explain why that is, but let us just look at the example that we had earlier. Okay, here we go. So, you see that here q is 2, n is 15. So, n is 2 to the 4 minus 1. So, that parameter m in this case, I may as well write it down here, that parameter m was equal to 4. And you can see here that the cyclotomic cosets, none of them is larger than 4, because no matter where you start, if you keep multiplying by powers of 2, eventually when you reach 2 to the 4, you will get back to where you started, because 2 to the m minus 1, 2 to the m mod 2 to the m minus 1 is 1. Okay. For that reason, your cyclotomic cosets are never going to be bigger than m. So, let us, since lambda 2 to the m mod n is equal to lambda 2 to the m mod 2 to the m minus 1, which is equal to lambda. Okay. So, that means that if you start from lambda and keep multiplying by powers of 2, after m steps you are going to be back where you started. So, the cyclotomic coset cannot contain more than m lambda. So, what you will do is you will go lambda, you will go 2 lambda, you will go 4 lambda, and then at most you might end up with 2 to the m minus 1 lambda, but at the next step you will come back to lambda. So, the size of your cyclotomic coset can never be more than m. Okay, so, that is one thing to keep in mind. Okay. And so, that is observation 1. The second observation, remember that we are looking for, we are trying to estimate the size of the null spectrum which contains these 2t consecutive zeros. The second observation is that the second observation is the following. If k in 1 to up to 2t is even, excuse me, if k is even, let us say that k is equal to 2l, then L is already in this set. And K and L belong to the same cyclotomic coset. So, I should let me write this differently, and K comma L belong to the same cyclotomic coset. So, what that tells us is that therefore, so what you are saying here is that look, I have 2t distinct elements here and I am worried about, I want to keep my, see the fact that I have 2t consecutive zeros guarantees my minimum distance is 2t plus 1. But now how large do I have to make my null spectrum to guarantee the presence of these 2t consecutive zeros? And the point is that you only have to ensure that the odd integers in this belong to the null spectrum, because the even ones come for free because of the fact that if you are picking cyclotomic cosets. So, if you pick L, you will also be picking 2L through that cosets. Therefore, it suffices to ensure that 1, 3, 5 all the way to 2t minus 1 are a subset of the null spectrum of the code, but the number of these is only t, right, because you start with t equal to, there are only 2, this set is of size C, this set is of size t. This set here is of size t. Therefore, the null spectrum need be no larger than m times t. Therefore, the dimension of the code, which is the size of the complement of the null spectrum, is greater than or equal to 2 to the m minus 1 minus m times t. For this reason, you will actually see that the parameters of a BCH code described in this way okay. So, this is how you would typically find the parameters of a BCH code described. And our earlier example here was of the same flavor, because this code here was actually a BCH code of minimum distance 5, because in that case you would insist that they would be the consecutive zeros would be 1, 2, 3 and 4, and by ensuring that 1 and 3 belong, you ensure that 1, 2, 3, 4 belong. So, the minimum distance is 5. So, in this particular case t was equal to 2. So, the size of the null spectrum was at most mt, which is 8 in this case. Therefore, the dimension of the code is at least 7. Okay, so, this is an example of that very same statement, and I am just going to quickly copy this slide over to that page where we were at, but perhaps I should just summarize. So, what we have done is that we have actually looked at so we had started out by looking at cyclic codes from a transform domain perspective, and so we defined this quantity called the null spectrum of a code. We made the link between cyclic codes and closed sets of frequencies strong by showing there is a one-to-one correspondence, and then we said, okay, now that we know how to design cyclic codes in the frequency domain, what can we say about the parameters? And the minimum the dimension is easy, it is just the number of frequencies outside the null spectrum. The minimum distance is complicated, but what we can do is, if we ensure there are a certain string of frequencies which are consecutive belong to the null spectrum, that the minimum distance is at least one more than the length of that string. Okay. So, that is kind of the BCH construction of cyclic codes. So, we use that to estimate the minimum distance, and what was behind that estimate is what I call the weight theorem, because it turns out that if a vector in the time domain has Hamming weight w, in the frequency domain its transform satisfies a linear recursion of degree w, and that is what enabled us to prove that. So, in the next class, what we will do next in final lecture, we will define Reed-Solomon codes and then quickly look at how one can actually decode these codes. Okay. So, we will stop at this point. Thank you.